I'm now going to introduce you to the first two principles of special relativity. So, the first principle states that the laws of physics are the same in every inertial reference system. So, what that means is basically that when you're walking on Earth and the Earth's at rest, it can correctly also be stated that you're at rest and the Earth is moving. That's both correct ways to look at it. That's an assumption. So, whenever Einstein says the laws of physics are the same in every inertial reference system, that's just it's stated as a fact and it's expected to be assumed to be true. So what it means is, let's say here is an inertial reference system and it's at rest. So it's called this 1, inertial reference system 1. The law of conservation of momentum for this reference system is just simply P1 plus P2, and it should be initial, dot, 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 P in initial is equal to P1 initial, final, not initial, plus P2 final, dot, 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 P in final. Such that for this specific reference system right here, reference system 1, it is such that P1 initial is equal to 0. So this right here is the law of conservation of momentum for reference system 1. So reference system 1 is at rest, so that means it's an inertial frame of reference, and the laws of physics are valid for this reference system. Or Newton's law of inertia is valid for this reference system, so every object moving relative to this reference system obeys Newton's law of motion. But like I said, this right here, what I have circled, is the laws of physics for this. It's the law of conservation of momentum for this reference system. And P1I is equal to 0 because the velocity is equal to 0. So this whole thing, where P1I is equal to 0, is the law of physics for this inertial reference system, which is at rest. Now, let's say there's an object moving relative to this at rest inertial reference system right here. We'll call it reference system 2. So it's moving with a constant velocity relative to inertial reference system 1, which means it is also an inertial reference system. And the laws of physics are valid in that reference system. Well, the first principle of relativity simply states that the laws of physics are the same in every inertial reference system. So this is inertial reference system 1. This is the law of conservation of momentum for that reference system. And the first principle of relativity is just stating that this law of conservation of momentum is the same for reference system 2. So it's stating as a fact that this reference system is at rest, and the laws of physics are the same for it. So all it is just being stated as a fact, and it's expected to be assumed to be true. It's just saying that basically it correctly can be stated that either one of these reference systems are at rest relative to each other while the other is moving. Those are both correct ways to look at it. In other words, when you're walking on Earth and Earth's at rest, that's one correct way to look at it, but can also be correctly stated that you're at rest and the Earth's moving relative to you. So Galileo first actually proposed this principle of relativity, and the way he presented it was, let's say there's the ocean and there's a ship on the ocean, and let's say you're inside a compartment inside the ship. Let's say you're inside the hold of the ship, and that Galileo said there is no experiment that you can do to conduct to prove that whether the ship is moving or is at rest. There's no experiment you can do to conduct. And that's basically just another way of stating the first principle of special relativity, that the laws of physics are the same in every inertial reference system. And by the way, every law of physics can be applied for every inertial reference system. So the law of conservation of momentum, the law of conservation of energy, mechanical energy, kinetic energy, potential energy, second law of motion, third law of motion, the E equals MC squared, all those. It just turns out that once you apply these principles, that you might have to write different versions of these laws. But They are essentially the same. So yeah, so that's that. Now the second principle of relativity comes from the first principle of relativity, and the second principle of relativity states that the speed of light is the same speed, or is measured to be the same speed relative to every inertial reference system, no matter the speed of the source of the light or the speed of the observer. So, in other words, no matter who is measuring the light, you always measure it to be the same speed. So, like, let's say this wasn't true. Like, let's say the speed of light is normally measured to be 3 times 10 to the 8 meters per second, which is what it is. And let's say here's a truck, here's a truck, and let's say somebody's standing on the side of the road right here, and this truck's moving relative to this person with a constant velocity. So when the light leaves this truck, if the speed of light wasn't the same in every inertial reference system, then the speed of light would go at 3 times 10 to the 8 meters per second plus the speed of the truck whenever it's measured by this person standing outside right here. And what it's saying is whether or not, like, let's say here's this truck coming this way, or like, let's say, let me draw a better picture. Uh, let's say here's a block and it's sliding towards the person right here, and let's say there's another block, it's sliding like this. So the speed of light coming towards this person right here would be 3 times 10 to the 8 meters per second, and right here it would be going 3 times 10 to the 3 times 10 to the 8 meters per second plus the speed of the block. But the second principle of relativity states that no matter what the speed of the sources of the light is, the speed of light is always measured to be the same no matter what. No matter what the speed of the source of the light is, it's always measured to be the same for every inertial reference system. So anybody that's in an inertial reference system always measures the speed of light to always be the same no matter what. It also says that the speed of the observer, even if the speed of the observer is some kind of different value, the measured speed of light is still the same for every for every light that's moving. No matter the speed of the observer or the speed of the source of the light, it's always the same. So, to understand why this comes from the first principle, let's go back to the situation of the ship in the water. And let's say you're in the hold of the ship. Let's say here's the walls of the ship. Now, the first principle can basically be stated as saying that there's no experiment that this person can do to conduct weather to tell that the ship is moving or it's at rest. So, like, let's say the ship was moving, and let's say we don't hold the speed of light to be constant speed or measured to always be the same speed relative to an observer. So, if that's not true, then whenever this ship is moving this way, then the light leaving this wall will be going faster than the light leaving this wall. So if you had some sort of detector to detect the speed of light, you can just simply measure the speed of light coming from this wall versus the speed of light coming measured from this wall, and you can see that if this speed is faster, then the ship must be moving this way. So also, if the observer is moving to the left or right, it would also affect whether you can tell if the ship's moving a certain way. So from the first principle, we say that there's no experiment you can do to tell whether the ship's moving or at rest. So what it is we hold the speed of light constant. The measure of the speed of light is always the same no matter what. It's always to be measured to be the same exact value, which is 3 times 10 to the 8 meters per second. And the reason how, we're going to talk about time dilation and length contraction and relativity of simultaneity in the future videos. But really, the reason how that's possible, that the speed of light is always measured to be the same speed, is because time dilates or length contracts, and relative to simultaneous events aren't always relative. Simultaneous events aren't always the same simultaneity relative to every reference system. So basically, like, let's say here's the speed of light in one reference system, so it's going to be d divided by t, and here's the speed of light in another reference system, d divided by t. So one reference system, like, let's say if time is not if time is not absolute, where it's not some kind of global time, everybody has the same passage of time or same sort of length of time. Uh, if you look at it where time is relative and not absolute, that it just depends on the observer, then you could say that, like, let's say this time would be 2 times larger than this. So t prime would be equal to 2t, and which means the distance must also be double, which that's not really length contraction, but that's just saying, like, if there's a double distance, that the time would be double. So that's that. So time can dilate and length can contract, and simultaneous events are not always simultaneous relative to every observer. And we're going to talk a little bit more about that in the future, but that's how it's possible for the speed of light to always be measured to be the same. Because time is not absolute, it's relative, and so is space. Space and time are not absolute, but they're relative. And there's no absolute motion. There's no absolute space or time. And that's the first two principles of relativity.